Page 5 of your packet. Yes, ma'am. There we go. All right, my darling. So I'm on page 5. We're doing 2.2p today. So we're still dealing with exponential modeling. This one in particular, so 2.2p, is all about doubling and half-lives. All right. So half-lives you probably know from if you did biology, you may have messed around with half-lives a little bit. All right. You also see it in chemistry with radioactive metals, things like that. Doubling, you definitely see in biology. It's strictly population. All right. So let's talk about this together. So we can model many physical phenomena. We know their percent increase and decrease per time unit. In this lesson, we learned how to be flexible with our exponential modeling. So, exercise 1 says a colony of fruit flies has a population that doubles every 8 hours. They were originally 22 fruit flies in the population. So, whenever they discovered the population, there was 22. Now, if P represents the population of fruit flies and D represents the number of times the population has doubled, we want to write a function, P as a function of D. So, thinking back to what we talked about yesterday, would this be an exponential growth or decay problem? Growth. So, what would my formula be? Just like the general formula. So, A equals P times 1 plus R to the power of T. Good. So, this is my exponential growth formula. So, we could still use this to describe what's going on. So let's go through and label what my variables are going to be. So A, P, R, T. Now they already said that A, or our accumulated value, is going to be represented by a P. That stands for population. Now, P in the growth formula, or the principal, would be what? So principal means what? Your what? Initial value. So what is my initial value for the fruit flies? 22. Now, this one, think about this carefully. What do you think my rate is? Just as a percentage. So, Jamie's kind of on the right track. He said 2. Why'd you say 2? Oh, someone said 2. Who said it? Oh, Tobias. Why'd you say 2? It's doubling. So, doubling typically means multiplying by 2. But what are we actually doing in terms of growth? What would our rate of growth be by? So, for example, if we start with 22 flies, how many is going to happen after 8 hours? So that's the first doubling. 44. After that? 88. So I'm multiplying by 2, but essentially I'm adding what? What percentage of the original? 100%. All right. So my rate is 100%. So when you say double, that's the same thing as saying 100%. That's your rate of increase. So as a decimal, 100 is what? 1. And then T, they want in terms of D.
It's a D.
D.
It's a D. She literally said it.
And that's okay. I told you my handwriting can be crappy, especially online because my pen sucks.
He should have been listening.
Dang, just called Jason out. Good Lord. All right. So now I got everything I need to put back into my formula. So I have P is equal to 22 times 1 plus 1 raised to the D power. All right. So that's the number of times the population has doubled. Now, if we simplify this part right here, it would be P is equal to 22 times 2 raised to the D power. All right. So this would be what we're talking about in terms of the population doubling. Now, remember, D represents the number of times that the population doubled. So in other words, we're saying that D is like if we said, okay, they doubled 3 times. How many hours would that have passed? If they doubled 3 times? 24 hours. All right. So D represents the actual doubling process. So we plug in a 3 here, that's how many would be after 24 hours. But that doesn't describe what would happen if they did just give us a random number. So for example, let's say 18. What if I said how much of the population is there after 18 hours? Well, can 18 even go into 8? Or 8 go into 18? No. So, but there's still an answer for it. So that's what the next part is going to discuss, how we can rewrite it in terms of the hours. So H represents the number of hours since the population was originally at 22. So it wants to write how H relates to D and D in terms of H. All right, so we're first going to write an equation for how H relates to D. So in other words, if we're talking about how many times it doubles, how would I know how many hours pass if it doubles? If I know how many times it doubles. So for example, I already used 3 as an example. So if we know that they doubled 3 times, how many hours pass? 24. How'd you get 24? 8 times D. All right, so 8 times 3, 8 times D. So H is equal to 8 times D. All right, we took how many times it doubled, multiplied it by 8. That's how many hours it passed. So if we doubled twice, how many hours passed? Doubled 4 times, how many hours passed? 8 times 4, guys. 32. All right. So now we need to solve that equation for D. So what's the only thing we got to do to get the D by itself? Divide by 8. So D is equal to H over 8. So we take however many hours we have, we divide it by 8. That's how many times we double. Now, there's a method to this madness. You'll see in a second. But, so part C is, using the answers from A and B, we're going to model the population of fruit flies P as a function of the number of hours since there are 22 fruit flies. So we're using both of these parts right here. All right. And how do you think I'm going to write this in terms of H instead of D?
One. Huh?
So guys, the original formula we came up with is in terms of how many times it doubled. So in terms of D. But how would I write that same formula in terms of H, or the hours that have passed? Don't we know what D equals?
H over.
H over 8. So what do you think I'm going to do?
Oh, put it in for H over A.
So all I'm going to do is take, since I know there's a D here, we know what D is equal to over here. I'm going to take this H over 8, substitute it in for D. So this would then be 22 times 2, H over 8 is equal to P. Did my thing disconnect? Because it wrote on mine. There it is. So all I did was replace the D with the H over 8, which is what we define D to be equal to in terms of hours. All right. So this would be our function in terms of hours. Does everyone understand what I did with that? All right. Now, the last thing that they want to know is by what percent is the fruit fly population increasing per hour? So we know that every time it doubles, it's doubling by 100%. But that's not the rate of increase per hour. All right. That's per 8 hours. So the way we would figure this out is we almost have to separate that exponent. So we still have P equals 22 times 2, but I'm going to separate the H over 8 into 1/8 times H. All right. So what we're saying is that in 1/8 of an hour, that's how much, that's our function. Now, through exponent rules, you can multiply this 1/8 or raise this 2 to the 1/8 power. So you can move this. So if this 2 has an exponent of 1, you can multiply the 1/8 and the 1 together. So this is the same thing as P equals 22 times 2 raised to the 1/8 power H. So now simplify that. So in your calculator, put in 2 raised to the 1/8 power. See what you get.
1.1 if you round it up.
Right. So if I put it in, I do 2 raised to the 1/8. Now I'm going to round it to, let's say, 2 decimal places. Or no. Let's do 3. All right. So it'll be about 1.091. All right. So if we round to 3 decimal places, it's 1.091. So P now equals 22 times 1.091 raised to the H power. So what we did, guys, is that we took this fraction and incorporated it into the exponent of our base. So that what I did is I created a new base so that now I know that in 1 hour, we're multiplying by a growth factor of 1.091. Now, think about the growth formula. I want to know the rate of increase per hour. So we're looking at this. If we're thinking about the growth formula, what part does the rate typically go into? In the parentheses. And what's typically in the parentheses? well, the part of the formula that's in the parentheses. 1 plus R. All right. So I want to look strictly at what's in the parentheses. And we know based off of the growth formula that 1 plus R is what's in those parentheses typically. So I'm going to set 1 plus R equal to 1.091. So if I solve for R, what's my rate as a decimal? Subtract 1. 0.091. That's equal to your R value. Now, what is that as a percent? 9.1%. You could have either multiplied that decimal by 100 or did the 2 decimal place move. So if I move this 2 decimal places to the right, my rate is 9.1%. So every hour, they're increasing by 9.1%. So we know they double every 8 hours, but we want to know how much they actually, what percent is actually doubling, or what percent they're growing per hour. It would be 9.1%. Does that make sense? All right. Now, why did we do all that? Well, it's just to show that sometimes not all of your growth is going to be in the units that they give you. All right. So remember, when we talked about growth and decay, T typically represented what time period or time frame? So we know T equals time, but what units was it typically given in? Years or hours. All right. So in other words, in terms of 1, so like 1 year's passed, 1 hour's passed, 2 years passed, 2 hours passed. That's what our variable represented. But this is a case where it's every 8 hours it doubles. So we need to know what happens every hour. And that's why we did what we did. All right, we started with the obvious, which was the doubling. Moved to writing that double in terms of an hour. And then we converted that to what would be per hour. All right, does that make sense? Kind of, sort of. So, guys, just to kind of reiterate, this is in terms of the number of times they double. This is in terms of the number of hours that have passed. So I can pick, so in other words, I can pick any number for that second equation. I can pick any number of hours and plug it in and still get a nice function. Whereas for the first one, let's say I had, over 9 hours. Well, how do I know how many times it doubled? All right. You would end up having to do 9 divided by 8 to figure out how many times it doubled. All right. All right, let's do another one. So, exercise 2. Now, basically what the lesson today is about is if we're talking about specific units of time, how do we convert it so that we can find it in another units of time? All right, so we're essentially converting units of time. So knowing what those different time frames are, that's very, very important. Okay. Now, this next one, a radioactive material has a half-life of 35 years. A of 0 represents the original amount of it present, and T represents the number of years it has been decaying. Which of the following models the amount A of radioactive material still present after T years? So we're going to essentially do what we just did, okay? But lot shorter process, all right? So first off, half-lives. So if I'm just talking about how many half-lives have passed. So if you've ever done chemistry or taken chemistry, you've probably heard about half-lives before. Okay? Essentially, all it's saying is that if you have, say, 100 grams of uranium, which is radioactive, after 35 years, there will only be 50 grams. That's still radioactive. All right? Another 35 years, 25 grams are radioactive. You're essentially dividing by 2 now. Okay? So, do you think this is going to be an exponential growth or an exponential decay? Decay. So, I'm using this formula now. Now, what do you think my rate would be? Just if we are, doing the actual half-life. So, every 35 years. If we do one half-life, 0.5. So in other words, we are decreasing by half every time the half-life is complete. So the rate for one half-life is equal to 50%. So in other words, your rate is 0.05. So if I have A is equal to A of 0, because we don't know what the starting thing is, we're just writing a function for it, times 1 minus 0.5 raised to some power of t. All right. Now, if I do 1 minus 0.05, what's left? 0.05. So automatically, these two answer choices are out. Because we know that what goes in this parentheses has to be 0.5. Now, let's say, for example, instead of t, I'm going to write x. Let's say x equals the time for one half-life, so 35 years. If I want to know how many years passed in terms of t, so t represents the number of years that has passed. All right, but the half-life takes 35 years. So in other words, if I wanted to figure out how much of the substance is still left after, say, 5 years, all right, would I have to divide that 5 by 35 or multiply that 5 by 35 to figure out the half-life? You'd have to divide by 35. So if it takes 35 years for the whole half-life to complete, that means that if we wanted to figure out in a certain number of years that are less than 35, we would have to divide it by 35 to figure out how much of the half-life actually completed. All right? So that means that we would replace x with t over 35. So if we do, we would get this. All right. Now, exercise 3 says if we use the same model that we just came up with for exercise 2, what would be to 4 decimal places our new b value if we basically did what we did back in letter D in exercise 1 for the decay per year? So we want to know what the rate of decay is per year. So we're going to take 0.5 raised to the t over 35. We're going to separate the fraction. So we now have 0.5 times 1 over 35t, which we're then going to raise that to. All right, so do 0.5 raised to the 1 over 35 power. Let's see what you get.
What are we rounding nearest to?
4 decimal places.
0.98. Yeah.
So 0.9804. So our new B value will be 0.9804t. And then whatever A of 0 is, and that's our new formula. Now, it asks us for the rate per year. So this table is now in terms of per 1 year, this happens. Okay? What percent are we decaying by? What? So would it be 98%? That's what we're decaying by?
0.98.
So would it be 98%? So if we convert this to a percent, 98% is not what we're decreasing by. That's how much is left over after a year. Right. So it should be around 0.02%. So remember, this represents this part of our formula, the 1 minus r. So all we have to do is just subtract 1 minus 0.9804. And that'll give us about 0.0196, which is 1.96%. So that would give us 0.0196. So that would be approximately 1.96% that we're decreasing. So every year, our radioactive material decays by about 2%.
Wait, why don't you just round it up?
Because it's blended 4 decimal places originally, so we gotta kind of keep it the way it is.
It's a percent, but you put so 90% rounded up, but it's oh.
Now, here's some vocabulary for you guys. This part is called your growth factor or decay factor. This part is called your growth dash decay rate. And what the difference is that this is the amount that you're decreasing or increasing per whatever cycle, so per year, per hour, whatever. Whereas this percentage here in the middle tells you how much is left over or how much you increased by. So if it was a growth, like if we go back to the very first problem, the population after 1 year would be, we would now have 109.1% of the population now after 1 year. Or 1 hour, whatever it is. Okay? Because it, increased. And you will be asked that on a test, guys. So know the difference between growth factor and growth rate. The rate is what you are increasing by. So think about the interest on a saving account. That's the rate that you're growing by. Where the factor is your total percentage that you have left over or that you have now. All right. All right. Okay, we're going to do one more and then we're going to go on break. All right. So hang in there. We're almost done and then we'll go on break. All right, so it's fairly common to move between times such as days, weeks, and hours. So, like I said yesterday, that's why you need to get in the habit of labeling your units because they can switch up on you. Okay. So, the number of people who know a rumor as a function of the days since it started is given by this function. Write a model for the number of people who know the rumor as a function for the number of hours it has been spreading. And then it wants to know at what percent to the nearest tenth is the rumor growing per hour. So they did the hard part for us. They already set up the original equation. Now we need to figure out what our new equation is based off of it being in hours. So this function right here is based off the number of days that have passed. We want to know the number of hours that have passed. So first off, how many hours are in a day? 24. So 24 hours is equal to 1 day. So if I know the number of days, which we're going to call D, how would I figure out how many hours have passed?
You would divide by 20.
So guys, how many hours are in 2 days? 48. How'd you figure that out? 2 times 24. How many hours are in 3 days? 72. How'd you figure out? So hours, if we want to figure out how many hours they are, we do, actually no, I lied. So if we want to know how many hours there are, we just do 24 times the number of days. So if I know how many days there are, how would I find the number of hours? Or if I know the number of hours, how would I find the number of days? Sorry, backwards. Divide by 24. So if I solved for H, or solve for D, this would be H over 24.
Did I not say that in the beginning? I said,
you know what? My brain's not braining completely right, so it's okay. So, since we know how to write our number of days in terms of hours, we can take this and replace it for D in our original function. So our new function would be n of h, because we're writing in terms of hours, is equal to 5 times 3.8 raised to the h over 24. Now, I now need to find my rate of growth. So how do I do that? So I want to get rid of the fraction part connected to the h. So I only have something raised to the h power. How do I do that?
You put 3.8 and then 1, and then with the parentheses, and then you and then 1. You put 1. I'm done. I can't.
No, I get what you're saying. So I separated the fraction from the variable. All right. I separate the fraction from the variable. And then I just put this put this exponent with the 3.8. So now I have 5 times 3.8 raised to the 1 over 24 h. And then I just need to figure out what this is. So what's 3.8 raised to the 1 over 24th power? Let's round it to 3 decimals. All right. So this would be n of h is equal to 5 times 1.057 to the h power. All right. So this is our new function. Now, based off of our growth factor, what is our growth rate? So 1.057 is our growth factor. So now I need my growth rate.
No, 100.
So remember, this is the same thing as 1 plus r. So all I got to do to get my rate is do what?
Add 1.
You can set equal to it, but in reality, all you really got to do is subtract 1. So if I subtract 1 from this, say just minus 1, that'll give you 0.057, which is what as a percent?
5.7.
5.7% growth per hour. So it grows 5.7% per hour. That's the other part. Any questions on this, guys?
Yes.
All right, so what we're going to do right now is we are going to take our 5-minute break. When we come back, we're going to do 2.2C. So today is going to be a long note day, guys, and I apologize for that, but we kind of have to condense some stuff because we took too long on Unit 1. All right. So go ahead, take your 5-minute break. I'm going to set the timer.
I got 10.
More like 10:22, but yeah.
I'm so sore. And like, so I just went to the back chance.
All right, guys, have a seat. You got less than 10 seconds. All right. Shh, shh, shh. All right, so back to the grind, guys. Nope. Got the one. Okay, so guys, I promise tomorrow you'll have a lot more work time, but we just gotta kind of play catch up a little bit. So we just kind of have to hit the ground running and finish up 2.2C today. Okay. So, all right, I'm now on page 9.
Wait, is 6, 7,
6, 7 would be the practice for 2.2B.
8 practice or optional? 6, 7.
Yep. 7, 8 is optional. Yeah.
She literally said
No,
it.
she said 7. All right. Shh. Now, still in exponential function land, still in taking word problem, turning it into exponential function. But now we're more in the banking world instead of the population world. All right. So, if you ever become a banker or have to deal with anything business, money, all that loveliness, all right, you'll probably see a lot of things like compound interest, your interest being compounded annually, bi-monthly, weekly, whatever. All right. This is how we deal with problems like that. All right. So far, we've only dealt with the growth and decay. So typically, in terms of the bank, we dealt strictly with just exponential growth, and those were typically compounded annually. All right. So per year, once per year. We're going to look at what happens if it's compounded more than once per year. All right. So, just to kind of get us started, we're just going to do this first problem using our exponential growth. Well, we already know about exponential growth. Okay? So let's set up the function for $500 invested at a 4% annual interest rate. How much is in the account after 1 year, 5 years, 20 years? So, using our growth function, so A is equal to P times 1 plus R to the T power. All right? We don't have an A value yet. So what's my P value or the principal? 500. 1 plus, what is my rate of increase as a decimal? 0.4. I mean 0.04. Sorry. And then raised to the T power, where T is in terms of years. All right. So after 1 year, okay, so kind of to save us some time on this, because we know we would do where T is equal to 1, T is equal to 5, T is equal to 20. All right. I'm going to use my calculator table to figure all this stuff out. Okay. So in my calculator, I'm going to go to y equals, clear out my two functions that are already there. And I'm going to type in the function that we just came up with. So 500 times 1 plus 0.04 raised to the x power. And then I'm going to generate a table so that essentially I have all the x values that I need in one convenient place. All right. So then I hit second graph. So at 1 year, $520. So after 1 year, I have $520. 5 years, looking back at my calculator, I have about $608.33. So $608.33. And then 20 years, right. So if we scroll all the way down to 20, 20 would be $1,095.60. So even though it says 0.6, we know in terms of cents, we would just add another zero after that. So this would be this. All right. Now, technically, what we just did was a compounded annually problem. All right. We're going to look at the problems when we compound monthly, compound weekly, compound bi-monthly. All right. We're going to look at the formula that helps us figure that out. So it's almost like we're taking what we learned in 2.2a and 2.2b and combining them. All right. But instead of doing all the extra work that we did in 2.2b, we have a nice, convenient formula. All right. So whenever you're dealing with anything compound interest, so it will flat out say the word. Boys, what are y'all doing? So it will flat out say the word. We grow at this rate, compounded monthly, compounded annually, compounded bi-monthly, whatever. All right. So this right here is the formula. Very, very similar to the exponential growth formula. The only differences are the ends. All right. These ends help us with when we compound anywhere more than annually. Because if we compound annually, it's just the growth rate formula. All right. So anything, so in other words, if we compound more than once a year, that's where our end comes in. So our variables, our first three or first four that we already know. So A, P, R, and T, they're the same thing. So A is your final amount. P is your principal, which remember that just is your initial amount. R is still your interest rate as a decimal. T is your number of years. Now, N represents the number of times it's compounded, meaning the number of times per year based off of its compounded. So, for example, if I said it's compounded monthly, how many times in a year is that? 12. 12 months in a year, it's compounded 12 times. If I say compounded bi-monthly, so bi-monthly, 6 every 2 months. All right. So bi-monthly means every 2 months. So for those of you with a job, a lot of times you get paid bi-weekly, every 2 weeks. All right. What about weekly? Remember how many weeks are in a year? 52. All right. What about daily? 365. All right. So you need to know what those words mean, guys. All right. So let's say we switch it up. So, for example, some accounts earn interest monthly, 12 times per year. All right. So the annual interest rate is divided by 12, and the exponent t years has to be multiplied by 12 to represent the interest being calculated 12 times per year. All right. So that's why the formula is what it is. That's why you're dividing the rate by n. That's the number of times the rate's happening. So basically, in 1 month, you divide the rate by 12. That's how much the rate of increase is for 1 month. Whereas with the time, you're multiplying it by 12 because you're compounding it 12 times per year. All right. Now, you don't really need to know the logistics of all that. As long as you know that formula, you're fine. Okay. So we're going to do the same thing that we just did for the warm up, but now instead of compounded annually, we're going to compound it monthly. All right. So our A, P, R, and T are still the same. So A would be A, P would be 500, R would be 0.04, and T would be T. But now we need to add our N. N is the number of times it's compounded. So if it's compounded monthly, how many times a year is that?
6.
A year. Monthly. 12. All right. So guys, don't overthink it. You guys know how many months are in a year. You guys know how many weeks are in a year. All right.
You said monthly, so I got confused.
Monthly. Once per month.
A year. 12.
Like I get paid
So how'd you get 6 the other time?
bi-monthly.
Okay, so
So now I got enough to put it into the above formula. So I have A is equal to 500 times 1 plus 0.04 over 12, because that's my n value, raised to the 12 times t power. So we're going to do the same thing that we did up top, and we're going to find when t is equal to 1, t is equal to 5, and when t is equal to 20, and compare the three. So I'm going to take that formula that I just came up with, plug it into my calculator. And to be honest, if you already plugged it into your calculator originally, you just need to make some minor edits. You don't really have to re-plug it in. So I'm just going to delete, 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 delete. All right. So I'm at this part. Now, whenever you put that fraction into your calculator, especially if it's in your TI, in Desmos, you don't have to worry about it, but in your TI, you definitely need to. You need to put parentheses around the fraction. So this would be 0.04 divided by 12. I mean, it's just so that your calculator doesn't invoke PEMDAS on you. All right. And then you raise it. I'm still going to put parentheses around this because I want to make sure my calculator doesn't try and PEMDAS their way out of this. 12 times x. All right. When in doubt, put parentheses around it because your calculator loves to do PEMDAS, and sometimes PEMDAS does not work in your favor, especially with functions. All right. So I'm going to hit second table. Now I'm going to work backwards a little bit. I already got 20. So that is $1,111.30. So this would be this. I'm then going to scroll up to 5. All right. Oops, too much. So $610.50. So after 5 years, that's how much I made, compounded monthly. And then after 1 year, it was $520.37. So based off of the 3 answers that we just got, how does that compare to the one that we did when we compounded annually? So the one we did up here. What happened? So between the ones we did up here, so here,
That one increased, and then that one also increased.
so you made more money when it was compounded monthly, right? So you made more money when you're compounded monthly, which is true. All right. So if you ever want to open up a savings account, like especially if it's a high yield, meaning high interest rate, or do anything with stocks, you want something that's compounded more than annually. All right. Because if it's compounded once per year, that sucks. Okay. Now, student loans, yeah, you want to compound it once per year. All right. So, but if it's something where you're earning money, you want to compound it higher than once per year or monthly. Now, that can be a good thing, but it can also be a bad thing. Where can it be a bad thing? Well, how many of y'all have a credit card? How many of y'all have to pay off your credit card? All right. What happens if you don't pay off your credit card every month? Interest rates. So, little life lesson for y'all. If you ever have a credit card, make sure you pay it off or at least pay your statement balance every month, because if you don't, whatever that interest rate is on that credit card, it gets added to your bill monthly. All right. It's compounded monthly. All right.
Credit cards at 16.
I think I have to have a parent like co-sign with you.
I was asking the teacher, not you.
So I think like 18 you can get one on your own, but if you're like 16, your parents have to co-sign. So yeah, sometimes it's a good thing, sometimes it's a bad thing, depending on what situation of money you're looking at. All right, so let's try a couple of these. Now, I know that you guys are capable of plugging it into your calculator and getting an answer. All right. I just want to make sure you guys can set up the formulas correctly. Okay. So, if we are compounding quarterly, so we start at $1,000, 3% compounded quarterly for 5 years. So again, we're using this formula. All right. So A would be equal to, what's my p-value here? $1,000. 1 plus, what's my rate as a decimal? 0.03. So 0.03 over my n value. So if I'm compounding quarterly, how many times a year is that?
4.
4. So then 4, and then how many years have passed? 5. So this would be what you would plug into your calculator. All right, you guys want to practice plugging it into your calculator, or are you good? Are you confident in yourself to plug it in correctly? So take a minute, plug it in. It's good. So guys, my suggestion is when you're putting it in, put parentheses around this part, put parentheses around this part. Okay? So again, I'll mark what I just said. You want to put extra parentheses around this part, extra parentheses around this part. So if you get an answer, round it to the nearest cent. So 2 decimal places. All right, who's got an answer?
Wait, give us like 5 seconds. They're all the same. They're all the same because they have the same value.
What? Huh?
Like they're all the same.
All I want to know is what the answer is for 5 years.
11,161.
11,000.
Shut
11,000. 11,000.
No, it's 1161.20.
Okay.
So sorry. You're not my mom.
Okay, $11,061.18. All right. Shh. We're almost done, guys. So now we're not going to plug this into the formula or anything, but compounded daily, what would your end value equal to? So how many times a year is daily? 365. Good. Now, I don't really want to deal with this table, but I just want you to know what you would plug in for your N. So specifically, this part right here is the important part. So it's the wording for compounding, and then what you'd actually plug in for N. So annually, you plug in 1, quarterly 4, monthly 12, daily 365. What do you think hourly would be?
1.
Hourly, how many hours are in a year?
1,600. That's my guess.
How'd you find it? 365 times 24. It's 8,000 what? 8,760. Because you just do 365 times 24 in your calculator.
Oh, I thought he did it in his head.
What's every minute?
You guys are so smart.
500,000 what? Yep. What about every second? I think it's somewhere in the millions. Oh, Lord. That's it? Okay. So, guys, you won't be asked hourly, minute, and seconds. Not with these problems. The most you'll be asked is daily. All right. So, if you know up till daily, you're fine. But that was just for funsies.
That was fun.
All right. Now, there's one other form of compounded that you need to know. That's called compounded continuously. Now, with compounded continuously, you get introduced to a new number. And that number is E.
What? That's not a number.
That is a number.
It's a letter.
You know how they said in math that letters aren't numbers? They lied. E is a number. Technically, pi is a letter too. It's just in the Greek alphabet. So, essentially, guys, a guy named Euler, all right, and his first name spells with an E, all right. He invented the number E, which is basically it's a number that kept showing up whenever they were doing any kind of exponential situation. All right. So the guy, you know, if you're a famous guy who discovers something, you get to name it whatever the heck you want. He decided to name it after the first letter of his last name, which is E. All right. Now, so this very special number is called E. Again, it's by Leonard Euler, a famous mathematician. E is used as the base in modeling exponential situations when it comes to continuous growth or decay. All right. So if you ever see the word compounded continuously, that's when you would use E. Now, to show you what E is about, in your calculator, they actually have an E button. So if you hit second and then the division key, that's E. Hit enter, it's about 2.718. All right.
It's like pi.
It's like pi. So like how pi is 3.14, E is 2.72. Or 2.718. I usually say 2.718. All right. Now, so E, just so you guys know, is approximately 2.718. Uh-huh. So you'll see when we get to logarithms, you'll see E again. But what happens is that when you're dealing with compounding continuously, you will use this formula right here, which is A time is equal to P E R to the T power. Where the A, P, R, and T are still the same thing. So P is your principal, R is your rate, T is your time. But remember, E is just a number. All right. E is not a variable in this case. It's a number. This is called PERT. All right.
PERT.
Like literally the short. If I say PERT, that means compounded continuously. That's how you remember the formula, PERT. It spells the word PERT. P-E-R-T. PERT. All right. So, just for little funsies. All right, we're just going to do one more and then we're done. I just want to do one compounded continuously. Okay? So, look at number 1 on the next page, letter D. All right? Shh. So, after 10 years, 15,000 invest in your account, 6% compounded continuously. All right. So whenever you see the word compounded continuously, so it doesn't say compound annually, daily, monthly, whatever, you use this formula. A equals P times E raised to the RT. So what would be my P value for this case? What did they invest initially? $15,000. What's my rate of the decimal? 0.06. Now, my time in this case is what? How many years did they say pass? 10. So if I plug this back into my function, this will be A is equal to 15,000 E raised to the 0.06 times 10. So if I were to put this in my calculator, watch this. Your calculator has an E value, okay? Especially if you want to raise it to the E value. So what you want to do is you're going to do 15,000. Then you're going to hit second. And then this key right here that says LN. All right. Above it, it says E to the X power. So it'll automatically have the exponent raised for you. So it plugs in the E, and now it has it raised to the X power. And what we want it raised to is 0.06 times 10. So compounded continuously, that'll be how much money we made after 10 years. So it'll be $27,331.78. $331. Oops. So guys, just know you need to know the formula for compound interest, which was the one that we did before this. And then if you ever see compounded continuously, you need to know what PERT is, which that's the easiest formula to remember. Because if you just remember the word PERT, you just got to know that it's compounded continuously. Now, biggest mistake that I see people make: do not use this formula if it's compounded in any other way besides continuously. All right. So a lot of people, because this formula is easier to remember, use this for any type of compound. So compound monthly, bi-monthly, whatever. So this is only for continuously. So if it does not say the word continuously, don't use PERT. Okay.
Wait, do we use it alone in this one?
A little bit. It's mixed in with everything else. All right, guys. So there's only about 10 minutes left. So you now have the ability to finish 2.2 Delta Math. Everything that's on it has been covered. So that'll be due. The tentative date will be tomorrow by midnight. Yes. Yeah. And then I will post your practice work. Yes. Give me 1 second. Okay, so I'll give you guys. So let's.